Hi everybody and welcome back to Miss Angler's biology class. I am Miss Angler. In today's video, we are going to do the introductory episode to population ecology, and this is going to be one of many videos I will make on this topic. Some of the other topics that we will still cover will be things like different types of growth curves, predator-prey relationships, and so much more. But in this particular video, we're going to look at what a population is, how to count it, and what are the factors that affect the size of that population. Now, if you are new here, don't forget to give this video a thumbs up and make sure your notifications are turned on and you're subscribed, because I post new videos every Tuesday and Thursday. So the first most important component of our understanding is what exactly is a population. So when we speak about population ecology, we are talking about a group of individuals that are the same species and they are found in the same place at the same time. And so that's why when we talk about populations, we can talk about populations that are perhaps in a country, like a country's population, but we can also talk about the human population too, and that's all the individuals together. Now, when we look at population ecology, we specifically focus in on the things that affect their numbers. So what is making the population bigger? What is making the population smaller? And there are four key components that you need to know and understand how they affect the population. Starting off with this picture here, we have a little group of small birds. Let's say they are a group of sparrows, and we need to see what affects their population. So the first thing we look at is births. Now, births have a positive influence on the population, which means that they add more individuals. However, on the other side, deaths is going to be a negative influence, and that then means that we minus individuals from that population. Then we have immigration. Now, immigration is often confused with its sister immigration, but essentially immigration is when individuals are moving into a population. So this has a positive influence on the population numbers, you adding individuals, whereas immigration is removing individuals. And a nice way to tell the difference is immigration's like exit. So it's leaving. Immigration sounds like in, like they're moving into the population. Now, an important component of population ecology is being able to actually count populations. But the problem is when it comes to counting organisms is that they don't all behave in an easy way for us to actually count them. And so we've got two main ways that we're going to learn now about how we can count organisms depending on whether they move around or if they stand still and make it easier to count. We're going to start off with organisms that move around, and we're going to start with the method of mark and recapture using a specific formula, and I'm going to use these snails to demonstrate how you actually calculate this. Now, what we do is we use this particular formula we see alongside, and you should always write this out in an exam because you always get like a mark for writing the formula. But let's break down the letters, and I'm going to show you how to apply it to our snail population here. So N is the estimated population, that's what we're trying to solve for. M is the total amount of organisms we captured the first time. C is the total amount of organisms we captured on the second time, hence the name mark and then recapture. And R is the total marked individuals that we caught on the second time that were already marked. And you'll see now what that looks like once I use it in this snail example. So applying it to our snails, let's say these are the snails that I have caught in my first grouping. So I've caught them now. And what I need to do is I need to actually mark all of them. So I would go along and I would mark each of them on their shell. And it's important, and you would need to know this also for tests and exams, that when you mark your snails, your animals, whatever you've caught, you need to make sure that the way in which you mark them doesn't hinder their movement, it doesn't hurt them in any way. And when you put them back into nature, you need to put them back where you found them or relatively close to that. And when you do the second capture, so when I go out again, let's say 2 to 3 days later, I need to do it in a very short period of time. I can't come back months and years later to do the second capture. So let's say, for example, I've gone out now and I've caught all these snails, and we have 1, 2, 3, 4, 5 by 4. So we've got 20 individuals here. So in my first capture, I have got, and let's put it into our formula, n equals 20 multiplied by, and now we're going to do our second capture. So I'm going to come back 3 days later, and I'm going to count my next group of snails. So I've gone out and I've caught my second group of snails, but you'll notice that this second group of snails has some that are counted and already have a little green mark on them, and then others don't. What I need to do is I need to again count the total population that I've caught the second time around. So the second time around, I still caught 20, but now we need to divide this number by how many individuals were already recaptured. So let's actually just count. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 snails that were already marked, which means that I've counted them actually for the second time. Now what you need to do is take this and calculate it in your calculator. Now this gives us a population of 36,36. But it's important that you don't leave the answer as a decimal, because you can't have like a third of a snail. You need to have a whole number. And so you actually need to round down, which I know conflicts with what we do in maths. We generally round up if it's more than or less than. But in this instance, we're always going to round down. It doesn't matter if this was 36,5, you must round down so you get a whole number. And so this is the estimated number of snails in this particular area of 36. Now the next counting method is what we call quadrat sampling. And basically we're using squares to count how many individuals are in that specific sample area. Now, quadrat sampling is great for organisms that don't move very much or are completely immovable, because you use a plastic or a metal square, a 1 by 1 meter square, to see how many individuals are inside of that square. And so when you place it down, you don't want them to be able to move very quickly, because otherwise they'll just walk over your quadrat and out of your area. So this is great for things that move slowly or don't move at all. One thing to keep in mind, though, when you are quadrat sampling, and you can have a look at the diagram on the left here, is if we are counting, for example, these crabs, you're going to count the crab that is mostly inside of the quadrat. If you get an individual who's on the edge or it's got most of its body on the outside, you're not going to count it. So in this example, you should know that there are 5 crabs in this quadrat and not 6. But let's actually apply it to the picture we see on the right-hand side, which is a representation of a field of sunflowers. Each one of those dots represents a sunflower. And I need you to know that one of these blocks is 1 by 1 meter, and it's going to form that square meterage that we see in the diagram. It's really important to figure out what it is. There are 10 by 10 blocks, so that means that this is 10 meters and this is 10 meters. And we need to know the size of the area we are working with when we do the calculation and when we calculate the estimated population size. Now, the next thing we need to do is we would take a random selection of samples of the quadrats. And so each of these squares represents 1 quadrat. And I'm going to select 5. 1, 2, 3, 4, 5, right? Those are our 5 random samples. And now we need to count how many individuals are in each. So in quadrat 1, we have 1, 2, 3. In quadrat 2, we have 1, 2, 3. In quadrat 3, we have, again, 1, 2, 3. In quadrat 4, we have 1 and 2. And in quadrat 5, we have 1, 2, 3, 4, right? So you're going to take all these individuals. Now you're going to add them to get a total. So we've got 9, 10, 11, 12, 13, 14, 15. So in total, we have 15 individuals. We are now going to take those 15 individuals and we are going to divide them by 5 to get an average of how many are in each of the quads, and that gives us 3. We then take that 3, and what we need to do is we need to multiply it by the total amount of quads we have, which was 10 by 10, which means we have 100, And that means our estimated total population size is 300 sunflowers. Again, everybody, if you ever get a decimal answer, you always round down. Now, once we start counting these populations, we can use them to plot graphs, and we can create a number of how many individuals we have over every single year, and we can start to see what the population is doing with its numbers. Now, it's interesting to know that when we do these counts, there is actually a maximum number that an ecosystem can support. And that's where the carrying capacity comes in. It is the maximum amount of individuals an ecosystem can support. And if it goes over that number, you often see a decline in the population. Now, what actually is the carrying capacity? It is everything from the resources available, like food, shelter, space, that creates a maximum number. And if we have a look at the graph here, we have time and we have the number of rabbits in a population, and then we have the carrying capacities. That's the maximum amount of rabbits that we can support. You'll notice in this graph, the number of rabbits starts to slowly increase and then dramatically increase because it's got lots of resources. And then when it gets to the top here, and it reaches the carrying capacity, it levels out, it flattens out. And that's because there are fewer and fewer and fewer resources, because there are more and more rabbits using those resources. But there's a little bit more to this story. If we look at the same graph again and we insert the carrying capacity here as the dotted line, the carrying capacity can actually move down and it can move up depending on how many resources and individuals there are. So what I mean by that is, if there are far too many individuals, the carrying capacity can move down permanently. And that's because you have removed so many resources that it can move down. However, if an area is opened up, maybe there is a new piece of land that now plants and animals can go into, and maybe humans have moved away from that area. So a whole new ecosystem opens up. That means the resources increase, and so the carrying capacity can also increase. But something also that maybe we are not aware of is, when we talk about carrying capacity, we must also know that the graph is never this smooth like we see in the first drawing. In actual fact, if this is the carrying capacity, when a population is approaching that line, so it goes slowly at first, and then when it gets to this top part of the carrying capacity, it often actually overshoots it. And what that means is there's so many individuals, they're rapidly reproducing, there's lots of resources, and then all of a sudden there are way too many of them. And what does that cause? It causes a dramatic dip in the population. Once it's done this overshoot, it actually self-corrects really well and doesn't drop all the way back down again. It will come back up and then level out a lot better. If it doesn't do this perfect leveling out, what can also happen is it can go up and overshoot and then fluctuate gently around the carrying capacity. And that's often the most common and realistic growth curve, is where you fluctuate slightly above and slightly below the carrying capacity over time. What we also need to talk about is, what is keeping the population curve below the carrying capacity? So what's pushing down on it when we look at these diagrams? And often in textbooks, you'll see these arrows pointing down, and that represents what we call environmental resistance. And environmental resistance refers to basically the limit of resources that are available in an ecosystem, and the environmental resistance resists the population growing. And so it does play an important role essentially in creating the carrying capacity. So just to clarify the difference between the two words, the carrying capacity is the maximum amount of individuals an ecosystem can support, and that carrying capacity is created by the environmental resistance, which is linked to the resources and the amount of resources that are available, and it is the force that is pushing down on a population, and it prevents them from overshooting the carrying capacity and staying above the carrying capacity. Now, what we need to also focus in on is these factors, these things that are influencing the size of a population, the things that create the carrying capacity, that create the environmental resistance. And that is where the density dependent factors come into play and the density independent factors. Now, when we speak about density dependent factors, the examples that we use are things like food, space, shelter, predation, and disease. And these are the things that are linked to density dependent because it depends on how large or how dense a population is. So sort of think of it like this. When we talk about the food dependency, right? If there are more individuals, so there's a higher density, there will be a greater need for food. Likewise, if there is more individuals, there's going to be actually more disease. So these are the factors that control a population, and they are based on how big the population is. Another one, for example, is predation. The more there is of prey, the more predators an ecosystem will then provide to maintain the population numbers. On the other hand, we have density independent factors. Now, these are factors that are not linked to the size of the population, and they are rather linked to natural phenomenon. And the two main ones are climate and natural disasters. So sort of think of it like this. It doesn't matter how many individuals there are in a population. The natural disaster that comes along, let's say it's a tsunami, the tsunami that wipes out the population, it didn't matter if it was a big population or a small population. So when we control that population size, it didn't matter how big it was independent. And this natural disaster occurs and it affects the whole population. Likewise with things like climate, so think like drought or floods. Again, that's not directly linked to the size of the population. If it's a big population, it's not going to create some kind of flooding situation. So when these independent factors occur, they are independent of how big the population is, and regardless of the population size, they will equally be affected. Every individual. There's no survival of the fittest necessarily. There is no bigger or better or adapted. They are all equal, and they all succumb to the drought, the flood, or the tsunami. Now, as always, I like to end off my lessons with a terminology recap, and you can use all of these terms to create flashcards and to study from, or to mind map out your ideas, or a blurting method is really good for this kind of thing, so you can write down the word and everything you remember about it. But we first of all looked at population, which remember is a particular group of organisms in the same place at the same time, and they are the same species. It's important that you know the difference between population and the definition for species. Then we looked at how birth and death have a negative or a positive impact on a population by adding or subtracting individuals. We also looked at how immigration, which is the movement of individuals into a population, versus emigration, which is individuals leaving a population, how they impact the overall population numbers. We looked at two methods that we count individuals. We use mark recapture for organisms that move around a lot, and we have to capture them more than once. We used a Quadrat method for organisms that are either really slow moving or they don't move at all, and we count an average and we get an estimate. We spoke about the carrying capacity, which was the maximum amount of individuals an ecosystem can support, and that carrying capacity is based off of the environmental resistance that occurs. That is when the environment resists the population's growth. And finally, we looked at the two types of density factors that can influence the size of the population, which was the density dependent, which is linked to the size itself. The bigger the population, the more problems, the less food, the less shelter. Whereas density independent factors are not linked to the size of the population and are rather linked to things like natural disasters, climate change, things that are not necessarily linked to the size of the population. Now, if you like this video, don't forget to give it a thumbs up and make sure you are subscribed with your notifications turned on because I post every Tuesday and Thursday. And I will see you all again soon. Bye.